Hey everybody, welcome to lecture 4.5 on linear approximations in multivariable calculus. In this video, we're going to learn about how to construct linear approximations similar to the tangent line in single variable calculus, except when we have multiple variables of input, we'll need something more complicated than the tangent line to approximate values of our function. We'll mostly focus on 3 dimensions where we have 2 input variables x and y and a single output variable z, in which case our 2 input variables will allow us to form a tangent plane, which has 2 dimensions or 2 directions of travel that will allow us to approximate values of that 3-dimensional function. So first we'll learn about the tangent plane and how to calculate an equation for that tangent plane. Think back a few videos to how we wrote down the equation for a plane in general in 3 dimensions, and this will be helpful for this video. Next, we'll learn how to understand the tangent plane formula as a linearization or a linear approximation. We'll also learn new notation for this using differentials like dx and dy that we've seen before. Finally, we'll learn about linearizations and how they can be used to estimate the value of a function, and also how to express this using the differential, which we'll talk about once we define the differential notation for a linear approximation. So to get started, what is a tangent plane? And again, in this video, we are only going to focus on 3 dimensions. In higher dimensions, there will be notions of tangent spaces, which could have more than 2 directions of travel like a plane does. In any case, if we have some surface, which we'll typically assume to be cut out by an equation z equals f of x comma y for a 2-variable function f, then the tangent plane to a point on that surface, I'll call the point x0, y0, z0, or a little quicker to read, is x0, y0, z0. And the tangent plane to such a point on this surface is a plane that contains all of the tangent lines to the surface through that point. Now, what does it mean to have a tangent line to a surface through a point? Well, there are a few ways to think about this. How do we define tangent lines in single variable calculus? We look at the curve running through that point, and we ask about the limit of the secant lines through the point, or more algebraically, we ask for the slope of the line to have a given derivative, the derivative at that point through the function, and to have the xy pair, the coordinate point lying on that line. That uniquely specifies the line. In 3 dimensions, we can actually do something similar using the notion of cross sections. So if we take a cross section of the surface, maybe this is our surface in the picture, that slices out some curve, such as the one in blue, then the tangent line to this blue curve, that's also tangent to the surface at a given point that's identified here as the black dot, will be one of the tangent lines that lives in the tangent plane. And if we take all of the different cross sections of this surface and look at all of the different blue curves that we can possibly draw, then the tangent lines at those points to those single variable curves, or those one-dimensional shapes, will form a plane's worth of different tangent lines. It's not always as intuitive as I would like it to be why we get a full plane's worth here. There's a little bit more of advanced mathematics behind why we get a plane. But if you think about it loosely, we have 2 directions of travel, kind of the x direction and the y direction in our domain. And likewise, on the surface, we have seen that we can compute 2 different rates of change, the partial derivative of the function with respect to x and the partial derivative with respect to y. And as long as those 2 values aren't really pointing in the same direction, which they're not if we use the x and y coordinates that point perpendicularly to each other, then we should get 2 different lines, and ultimately these will span a plane's worth of tangent lines. To state things more algebraically, we're going to use the following formula for a tangent plane at a point x0, y0 in the domain of our function. So if the graph of our function has a tangent plane at a given point x0, y0, then the equation of this plane reads as follows. Now, this is an equation involving x, y, and z. All of the z0, x0, and y0 values are actually specific numbers that we would plug into this equation, and the only variables left over are x, y, and z. So that was just a preface before I read the equation, but now here it is. Z minus z0 is equal to the partial derivative with respect to x, evaluated at the point x0, y0, times x minus x0, plus the partial derivative of the function with respect to y, evaluated at the point x0, y0, times y minus y0. I want you to stop for a moment and think about what this formula looks like to you, what each piece of the formula means, and how you would go about computing the coefficients and the different terms in this formula. And also think about why this is an equation for a plane. How does this compare to what you learned a few videos ago for planes in 3 dimensions? I want to point out one thing that makes it a little bit easier to remember this formula. If we covered up the entire first term involving x things, you'll see there's an x naught here, but all of the things involving the x variable, the partial with respect to x, and then the x minus x naught term. And we just had this second piece here. Or if we set the other thing equal to 0, for example, then we have an equation that looks like z minus z naught equals some slope or rate of change times y minus y naught. That would be exactly the equation for the tangent line, in this case, the tangent line in the x or in the yz plane through the point y naught z naught. The way you can achieve this, by the way, is by plugging in x equals x naught. So at a certain coordinate, for the x value, the y and z values are allowed to vary still, and we get an equation for a tangent line. That's one way of recovering just one of the tangent lines in the previous picture. If this were the, yeah, this actually looks like the right one. This blue curve is changing in the y direction, has an x value fixed, and at that given point, this tangent line that I'm highlighting here in gold, the shorter one in the picture, is given by evaluating this formula for a particular x coordinate. Now, of course, we could play the same game, let the whole second expression go to 0 by plugging in y equals y naught. We have an equation, z minus z naught equals slope times x minus x naught. That's another equation for a tangent line. And by varying these equations, by plugging in different x and y values, we can obtain the other tangent directions, or tangent lines sticking in different directions. So this in general is the point slope form of a plane, where our x and y slopes, which we denoted by mx and my in a previous video, here are actually the values of the partial derivatives fx and fy at the given point. So this is a special type of plane in 3 dimensions. It fits our general plane formula, and the coefficients we compute are obtained by computing partial derivatives and evaluating at a particular point. Not all planes are of this form, or really all planes are of this form, but it might not be obvious what curves they are tangent to, those particular planes. So in general, if we have a plane, it's not necessarily a tangent plane on face, but for every curve, or rather, for every function, f of xy, we can look at the surface, z equals f of xy in 3 dimensions, and we can construct tangent planes at every point, assuming that the partial derivatives exist at those points. So we'll do an example in a moment, but if we unpack the 3-dimensional picture into cross sections like I was explaining a few slides ago, and we actually plug in those y or x values, as I've shown you here, this is algebraically what I just mentioned on the previous slide. We actually get an equation for a tangent line in each situation, but graphically, visually, this is what's happening. Those gold lines that were shown, I'll show you the slide again. The gold lines that are shown crossing through the point here can be picked up, skipped around a little bit, can be picked apart using different cross sections of the figure. These are the 2 cross sections. The left one is by holding y constant and letting x and z vary. And we get a single tangent line given by the, or with slope given by the partial derivative with respect to x. Likewise, if we hold x constant, we look just at the y-z direction, we'll get a different tangent line, potentially with a different slope. So let's do an example together. Let's give an equation for the tangent line to the following function at the point 4, 0. You have the tools to do this on your own, so if you want to pause the video and try to at least work out the different terms in the tangent line equation now, I encourage you to do so and then check back in with me once you've figured out some of the pieces. So let's get cracking. Here I've reproduced the formula for a tangent plane in general, and you see that I've actually scooted one part over to the right side. Instead of z minus z naught, this is z naught. That's the z value when we plug in the point x naught, y naught, by the way. I've scooted that over to the right side, so we have an equation solved for z. So z equals what we think of as the constant term, or the height of the function when we plug in x naught, y naught, plus slope in the x direction at our point, times x minus x naught, plus slope in the y direction at our point, times y minus y naught. This is an equation for the tangent plane to the point x naught, y naught, and here we want to plug in 4, 0 everywhere we see x naught, y naught. So I'm going to break this into a few computations. The first piece we have is what's the value of the function at this particular input value. And the function here is square root of x times e to the y. If we plug in x equals 4 and y equals 0, we'll see that we have 4 times e to the 0, and take the square root. E to the 0 is 1, square root of 4 is 2. So we get a z value of 2. Next, let's compute the x partial derivative, and then we'll plug in the point 4, 0 to get the x directional slope of this tangent plane. So the partial derivative here, this is actually a chain rule problem. And I see, first of all, that the function inside is x times e to the y. Y is a constant with respect to x. So I just have that constant coming out front as the derivative of the inside. If you want to pause and double check this for yourself, just remind yourself what it means to take a partial derivative, in this case with respect to x. We'll be doing the y1 in a moment together. It's a chain rule problem, so I need to multiply by the derivative of, so I've multiplied by the derivative of the inside, and I need to do the chain rule. So the square root is 1/2 power. I'll bring down the 1/2 and drop the power by 1. And just for the sake of being able to plug things in, I'll rewrite this as follows. This is e to the y in the numerator and a 2 square root of x e to the y in the denominator. So this can be simplified, but this is good enough to evaluate the function, this partial derivative at 4, 0. If I plug in, again, let me just plug all the things in so we can see them. 4 e to the 0. All of the e to the 0s are just 1. So I really have 1 over 2 times root 4 is 2. So that's going to give me 1/4. And that's going to be the slope in the x direction, or the slope of the tangent line through 4, 0 if I hold the y value constant and equal to 0. Okay, next let's do the partial derivative with respect to y. I need to show you the function again. It's square root of x times e to the y. And here, x e to the y, x is a constant. So you can think of this as like a function constant times e to the y with respect to y. Now again, it's on the inside, so this is a chain rule problem. But the derivative in that case is the exact same exponential expression. Sorry, I have a typo. It's x e to the y. And now we'll do the chain rule again. Bring down the 1/2 power. X e to the y is now raised to the minus 1/2. And for convenience, I'll write this as a fraction once again. Oops. 2 times the square root of x e to the y. That's all under the radical, by the way. Good. So I think we're done with our function. We just need to assemble all these pieces in a moment. Let's plug in 4, 0 into this piece to get our y directional tangent slope. So in the numerator, I'll have 4 times e to the 0. In the denominator, it's actually the same denominator, so 4 e to the 0 there. And here I have 4 over 2 times square root of 4 is 2. So I'll just get a y slope of 1. I said this out loud, but just to remind you, this is really our mx, and this is our my from a previous video for the general form of a tangent equation. And then the intercept is given by, well, the intercept can be solved for in general, but this is really the key piece of information we need to write this whole point slope form down. So let's write out the tangent plane. I'm not going to scroll up to show you the form. I'm just going to say it out loud as we go, and it should start to feel familiar, especially if you remember a lot of single variable tangent line approximations. So the tangent plane is going to be z minus the z coordinate. I'll push it to the other side, and our z coordinate was 2. So we'll have 2 for the constant term. And then the slope with respect to x, or the mx slope, was 1/4 times x minus the x coordinate, x minus 4, plus the y slope is next. That's 1 times y minus the y coordinate, which was 0. So I'm just going to write plus y for the last term. So here's our tangent plane equation. And this now can be used to generate approximations or compute approximations to the values of the function square root of x e to the y at points nearby 4, 0, just like we can use tangent lines for single variable functions to approximate heights of the function in the xy plane using points nearby on the tangent line. We'll actually do this in a moment. This is the example 454 that you see starting at the bottom of the screen, but first I want to build up to this using general theory. So we've successfully computed the equation of a tangent plane to a function at a point. What can we do with this? So just like in single variable calculus, we can treat the equation for a tangent line as a linearization of a function. Linearization literally means form a line out of, or make into a line. Linear meaning line, and the rest means, do something to your function. So linearization in this case doesn't mean form a line. We actually have two different dimensions of input values, our x and y coordinates. And linearization is a word that in higher dimensions means form a space out of. In general, a vector space if you've taken a linear algebra course. But in this case, we'll form not a line, but a plane. That's our linearization. So the plane here is actually exactly what I did in the previous example. It'll be z, or we can call this a function of x and y, L of x comma y, is equal to the z coordinate at our point, that's f of x naught, y naught, plus, now the rest of this is identical from the tangent plane description. So if our graph, again, is of the form z equals f of x comma y, and we can compute its tangent plane, we can unravel it by solving for z, or solving for what we'll call L of x comma y, and treat this as a function that inputs x and y values, and the outputs are approximations to the values of the function at those xy coordinates. As long as we're close enough to x naught, y naught, we'll get a good approximation. Later in the video, we'll talk about how to actually understand the error in such an approximation. This is something that was probably not done explicitly in your single variable calculus class for the tangent line approximation, but it's something you can do in practice using derivatives, and we'll see how to do this with tangent planes in a moment. So to practice with this linearization technique, let's actually do the next example together, where we approximate the value of this nasty looking square root expression using what we learned in the first problem a moment ago. So I'll show you that expression again. Let's use a linearization to approximate the value of square root of blah, 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 some stuff. I want you to notice, first of all, this value, and this is a number, square root of 4.02 times e to the 0.05. That's the square root of some positive number. It's well defined. And it's actually pretty close to what would happen if we plugged in the x and y values 4 and 0. So 4.02 is a little past x equals 4, and 0.05 is a little past y equals 0. So this is pretty close in input values to 4, 0, and that means that the output values should be pretty close to the output values of the function if we don't stray too far from our coordinates 4, 0 that we already computed a tangent line for, or a tangent plane for. So using the notion of a tangent plane, which says it hugs the curve or hugs the surface pretty closely when we're near to the point that it touches at, let's use our tangent plane from above to get a decent approximation to this numerical expression, square root of this chunk. Again, remember that this is equal to 2, so we already know the value is going to be somewhere close to 2. The height of the two-dimensional function is 2 at 4, 0. So we're probably already thinking this is going to be somewhat close to 2. We just want to see how close it actually is. So let's use our tangent line, or sorry, our tangent plane again, which was z equals 2 plus 1/4 x minus 4 plus y minus 0, or just y. I believe that's what it is. Let's scroll this to double check. Yeah, 2 plus 1/4 x minus 4 plus y. And let's actually use this and think of this as a function, L of x comma y, where we're now able to plug in x and y values to get approximations. So I don't want to plug in 4, 0, by the way, because this would go to 0 and this would go to 0. We just get the value of 2, which we already know from our computations above. Instead, I want to plug in new x and y values that will help me approximate this expression. So my x value is going to be 4.02, and my y value is going to be 0.05. These are the nearby x and y coordinates we want to plug into this plane equation to determine a z value, which will approximate the function value at that set of coordinates. So let's do it. So L of 4.02, 0.05 is given by 2 plus 1/4 4.02 minus 4 plus 0.05. And we can use a calculator to evaluate this. That's fine when you're working on the homework. We can do this one by hand because it's not so bad. This will be 1/4 times. The difference here is just subtract away the 4 pieces and get 0.02. And luckily, we're only dividing by 4, so this isn't so bad. If I divide by 2, I'll get 0.01. If I divide, or 100th, if I divide by 2 again, I should get 0.005. And you can check this with a calculator if you're not super comfortable doing these by hand. In any case, I have some decimals that are easy to add up. I'll have 2.055. So the value of the linearization, or the tangent plane, at 4.02.05 is equal to 2.055. That's pretty close to 2 like we expected. But this also tells us that this true value of the square root of that junk is fairly close to 2.055. That's a good approximation. How good is it? Well, let's learn more about linearizations and tangent planes and differentials to say something a little more precise. So we've learned about differentials like dx and dy in the past for integration mainly, but it's supposed to represent the infinitesimal change, or the change really, really close to a certain x or y value of that variable. Dx is the change in x, dy is the change in y. We start taking ratios like dy over dx. That actually tells us about rates of change, which is related to the derivative. And when we have multiple variables, we usually denote things using partial derivative symbols or the partial derivative of your function. The differential dz also makes sense. This is the change in z, or it's some infinitesimal notion of change of the variable z. And if x and y are changing and z is dependent on those input variables x and y, then the differential dz can be expressed in terms of the differentials of x and y respectively. And it's nice to actually use the following shorthand when we're trying to estimate error, but it also has uses for other things like integration in multiple variables, which we'll learn about in another chapter. But the following notation is something that's useful to understand the linearization, the tangent plane linearization for these three-dimensional problems. So here's the following note, or here's the notation that I want to talk about as follows. So if z is written as a function of x and y, then the differential, sometimes also called the total differential, dz, is a function of our point x naught, y naught, and two independent variables, dx and dy, all of which can be specified by plugging in the point x naught, y naught, and or plugging in the rates of change dx and dy to get out a value for this dz expression. So if you go on and take more math courses, this is actually not the rigorous definition of a differential, but in any case, this is close enough for our purposes. And symbolically, we can write it either dz as the partial derivative at x naught, y naught times dx, plus the partial derivative at x naught, y naught times dy. And for shorthand, it's useful to write this as dz is equal to the partial of z with respect to x times dx, plus the partial of z with respect to y times dy. Notice that this is exactly the same as the tangent plane formula, where if we replace dz with the expression z minus z naught, you can think of that as the change in z nearby z naught, dx and dy as x minus x naught, y minus y naught, respectively. Then this is exactly the same as the tangent plane formulation of linearization. Why this is useful is we can actually use it to bound the error in a linear approximation or in a tangent plane approximation to a multivariable function. So here's a problem that probably feels familiar from Calc 1, trying to use angles and trig to estimate different rates of change in some geometric picture. I'm not going to draw the picture again, but you've probably heard the height of a pole. Maybe there's a person standing and there's a light being cast on them by a lamp pole and their shadow is changing at a certain rate. But we can actually ask about, in this case, the person's not walking, we're just asking about the height of the pole being measured from some distance away, just using visual geometry. So the function in this case, let me actually switch over to the version I can write on. So the function in this case that measures the height of our pole is given by h for the height is equal to b times tangent of theta, where b is the distance we're standing away from the base of the pole, and theta is the angle made by the ground and the top of the pole. This is a trig problem that you can draw pretty easily using a triangle and see that b times tan theta is the correct value that relates all three of these variables, b, theta, and h. Now, if we're allowed to walk different distances away from the pole and compute this, then the height is technically a function of the base and the angle that we're making. So that the base meaning the distance that we walk away from the pole, and theta, the angle that the ground makes with our perspective up to the top of the pole. So this is a multivariable function, and we can ask, how do we express certain values of h by specifying what we know at different bases or different distances away and different angles theta? And can we get an accurate approximation to the height of the pole using different places that we stand? So first of all, let's try to anchor ourselves and just compute the height of the pole at a fixed base and a fixed angle. If the distance to the bottom of the pole is 13 meters and the angle of the incline is pi over 6, the height of the pole is simply computed by plugging in these values. B times tan theta here is 13 times tan of pi over 6. And if you remember from calc class, tangent of pi over 6 is given by root 3 over 3. So just writing this as a single fraction, 13 root 3 over 3 is the height of the pole. Now, we may not know exactly what that value is without using a calculator, but suppose we do know this exact number. Actually, I'll tell you this exact number just so we have something in mind. This is about 7.5. And suppose we use this as an approximation to the height of the pole. If we get an exact reading of 13 meters away from the base and an exact reading of pi over 6 radians of angle, then we'll know that the exact height is this 13 root 3 over 3 number. But in general, measurements are not made with utter perfection. So our maybe our reading off the tape measure for how far we stepped away from the base of the pole could be off by a little bit. Let's say it's off by at most a tenth of a meter. And our measurement of theta, which might be more difficult in general, we'd have to use some sort of trigonometry to evaluate. That could be off by, let's say it's off by at most pi over 120 radians. That's not too much of an error for the angle. But in any case, if we allow our measurements of the base of our triangle and the angle in the triangle that's formed by where we're standing and the top of the pole to have a little bit of error, we can actually say how close to 7.5 we actually are, or rather, how far away from 7.5 the actual value could be. So the way that we do this is by computing the differential. Here, our function h is a function of b and theta, the base and the height of the triangle. So our differential for h can be written dh is equal to the partial of h with respect to b times db, plus the partial of h with respect to theta times d theta. Let's go ahead and compute each of these coefficients. These are exactly the coefficients in the tangent plane representing h as a function of b and theta at any given point, and we can actually plug these things in. So dh db, or rather partial h partial b in this case, the rate of change of h with respect to b, since our function is b times tangent theta, is, let me actually just write that again. So we'll need it twice. H is b times tangent theta. If we compute the derivative with respect to b holding theta constant, well, tangent theta is a constant and b is just raised to the 1 power. So we'll just get tangent theta. This is a function of b and theta, but you see that only theta actually appears. On the other hand, the derivative of h with respect to theta, now b is a constant, and tangent of theta has a derivative, which is secant squared. So b times secant squared theta is our partial derivative of h with respect to theta. So at the point, that we plugged in, b theta is equal to, sorry, I actually forgot the point. What was our point? 13 and pi over 6. So at that given point, let's see how close to the true value of the pole we are guaranteed to be given these error tolerances for the base and the angle measurements. So if we plug these values in to the differential expression, partial h with respect to b, which is tangent theta, evaluated at 13 comma pi over 6, is just given by the tangent of that angle, which is √3 over 3. And that's times dB, that differential. On the other hand, evaluating the partial of h with respect to theta, that's b secant squared theta at pi over 6. We should probably do that one. We should write this one out. So at 13 comma pi over 6, we'll get 13 times, let's see, secant squared is 1 over cosine squared. The cosine value at pi over 6 is, well, I need to think on my unit circle. So the cosine at pi over 6 is going to be √3 over 2. And if we square that, we'll get 3 over 4. And secant is the reciprocal of that, so 4 over 3. That's going to give us, let's see, 52 over 3. So 52 over 3 is the slope here, the change in h over the change in theta times d theta, that differential. So here's the trick. This expression is just a repackaging of the tangent plane formula. But if we allow our b measurement to be off by at most 0.1 meters and our theta measurement to be off by at most pi over 120 radians, we can say how close or how far off the h measurement was using those values by plugging them into the formula, into the function. So if if b is off by at most 0.1, then the change in b as we move away from our b value of 13 is at most 0.1. You should think of the differentials as measuring error, in other words, or the distance away from the true value. On the other hand, theta, if theta is off by at most pi over 120, then this is actually an expression that bounds the error in our dH differential or bounds the error in our H calculation. I'm going to quickly plug this into an online calculator so I can give you a numerical answer, but in general, this is as far as we could go. In particular, I don't want to estimate the pi over 120 part with any precision by hand. So numerically, this is something close to 0.5115. So the true value that we got previously, using those estimated or observed values of b, 13 meters, and theta, pi over 6, was about 7.5 for the height of the pole. And we are certainly within 0.5115 meters of an accurate calculation. So you could also, so the height of the pole is in the interval it's definitely in the interval, let's see, 6.8. I'm going to be able to do this by hand. Probably not. My mental math is a little slow tonight. So subtracting and adding this DH bound 0.5115 would give you the following expression. 0.15. So we definitely know that whatever the height of the pole is, this is the range of possible heights given our approximation and our error tolerances for the measurements b and theta. How would you use this in practice? Well, if you're using different measured quantities, in this case b and theta, that you understand a little more simplistically how the possible error works, and you're using those together to estimate the value, in this case h, of some other quantity in the picture, then those errors can be combined using the differential formula dh equals this expression in terms of dB and d theta to get an error estimate for the total approximation of height. So let's wrap things up in this video. Getting back to our slides, here are a few summary questions, and then I'll leave one applied problem, a word problem as this one was on the previous slide for you to work out on your own. So here's some summary questions for you to think about. If you want to write down the equation for the tangent plane to a function or a graph z equals f of xy at a given point, what do you need in order to compute what do you need to compute in order to write down this tangent plane equation? Next, for what kinds of functions are linear approximations useful? How are the tangent plane and the linearization of a two-variable function related? And finally, how is the differential defined for a two-variable function? And what does each variable and even each expression in that differential formula mean? And finally, I'll leave this, this problem from the book for you to think about on your own. This is another applied problem, and you have a multivariable function describing the compound interest when you put money down and purchase a home, or in this case, if you put money down into something like an annuity or a savings account and later use it to purchase a home, the compound interest earned on your initial investment of $10,000 can be modeled using this multivariable function. We'll talk about some more examples in class, but thanks for tuning in, and I will see you next time.